Your services are timing out with 30-second delays, readiness probes pass, but DNS resolution fails. The culprit? A default deny egress policy that blocks all outbound traffic, including DNS to CoreDNS. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover Kubernetes network policies. Imagine your apartment building has no locks on any doors. Every tenant can walk into every other apartment freely. Kubernetes without network policies is exactly that. Every pod can talk to every other pod by default. Network policies are the deadbolts you install. The API server stores network policies but never enforces them. Enforcement lives entirely in your CNI plugin. If no policy selects a pod, all traffic is allowed. Once any policy selects it, all unpermitted traffic is denied. A default deny baseline is the foundation. This policy selects all pods in the namespace and blocks all ingress and egress traffic. You then add explicit allow rules for exactly what your application needs. Here's the default deny policy. The empty pod selector matches every pod in the namespace. With no ingress or egress rules, all traffic is blocked. This is your zero trust baseline. The most common production incident: applying default deny egress without a DNS carve-out. Every DNS lookup to CoreDNS on port 53 is blocked, causing 30-second timeouts on every service discovery call. Always add this egress rule to allow DNS traffic to CoreDNS. It targets the kubesystem namespace and the kubeDNS pod on both UDP and TCP port 53. Ingress rules control inbound traffic. Egress rules control outbound. The YAML indentation is critical. Multiple selectors in the same dash entry are AND'd, while separate entries are ORED. This policy governs the API server pod. It allows ingress only from front-end pods in the web namespace on port 8080, and egress only to Postgres on 5432 and CoreDNS on port 53. The difference between and or is determined by YAML indentation. A single dash entry with both namespace selector and pod selector requires both to match. Two separate entries allow either match. The ipBlock selector is the only way to restrict traffic to external IPs. However, if your pods go through a NAT gateway, the source IP seen by the destination is the NAT gateway's IP, not the pod's IP. Never trust that a network policy is enforced without empirical testing. Use kubectl run with a curl image to test connectivity. A timeout means the CNI is dropping packets correctly. A connection refused means the policy is not blocking. This command runs a temporary pod in the web namespace and attempts to reach the API server. If it times out, the policy is blocking correctly. If it gets a response, the policy allows the traffic. This is the same issue we highlighted at the start. Here's exactly why that happened. The team applied a default deny network policy with both ingress and egress in policy types, but no egress rules. This blocked all outbound traffic, including UDP and TCP port 53 to CoreDNS. Every pod in every namespace could no longer resolve DNS names. The fix was to add an egress rule allowing traffic to kubesystem/kubeDNS on UDP and TCP port 53. We also created a namespace bootstrap template that always includes the DNS carve-out, and added a CI check that validates every network policy with egress in policy types has at least one egress rule targeting DNS. This is the exact policy that caused the incident. The policy types includes egress, but no egress rules are defined, meaning all outbound traffic is denied, including DNS. Always add a DNS carve-out. This rule requires the source to be in the web namespace and have the label app, front-end. If you intended OR, you need separate dash entries. The indentation is load-bearing. Pods with hostNetwork. True bypass all network policies because their traffic is not on the pod network. Never run critical workloads with hostNetwork unless you have node-level firewall rules. The CNI controller, e.g., Calico Cube controllers, or Cilium operator, must be healthy for policies to be translated into kernel rules. If it crashes, existing rules persist but new policies are not applied and deleted policies are not removed. Monitor the CNI controller's health as critical infrastructure. Run this command to confirm your CNI plugin enforces network policies. If only Flannel is present, policies are silently ignored. Pods with hostNetwork. True, bypass all network policies because their traffic uses the host's network stack directly. Never run critical workloads with hostNetwork. True, unless you have node-level firewall rules. Use admission webhooks to reject such pods in sensitive namespaces. To debug network policy issues, start by testing connectivity directly with curl or enslookup from a pod. Check if your CNI supports policies. Inspect the policy YAML and verify pod labels match selectors. Let's run through some common interview questions. How do network policies handle existing connections? They don't kill them. Contract keeps established flows alive until timeout. What is the difference between and or in policy selectors? Same dash entry equals and, separate entries equals OR. Why does default deny egress break DNS? It blocks UDP TCP port 53 to CoreDNS unless explicitly allowed. And a few frequently asked questions. Do network policies apply to same namespace traffic? Yes, they apply to all pod-to-pod traffic regardless of namespace. How do I allow traffic from external IPs? Use ipBlock selector, but be aware of NAT and set external traffic policy, local if needed. Can I use a policy to deny traffic? No, standard network policies are additive whitelists only. Use CNI extensions for deny rules. To recap, network policies are declarative contracts enforced by the CNI. Start with default deny, then add explicit allow rules. Never forget the DNS carve-out. Always test with real probes. And for large clusters, consider eBPF-based CNIs like Cilium for better performance. Ready to go deeper? Up next, Service Mesh, then Introduction to CI/CD, then GitHub Actions tutorial. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.